Hi everybody, this is just an answer to one of the questions on Doppler effect, and this is question number 2. Now, Doppler effect can also be applied to the universe, to the galaxies, to stars, and there is a theory, you've heard about the Big Bang theory. So what's that all about? It's about the expanding universe. So do we have any proof that the universe is expanding? Doppler effect is there to come to your aid. So what happens is that the galaxy is made up of stars, so there's light from distant stars and they reach the earth. Now, as you know, light is also travels in the form of waves. So if the star was stationary, the color of the light emitted by the stars, when you look at it through a diffraction grating, you can see what's called spectral lines. Okay, you can split it all up into spectral lines. And so if you compare the spectral lines of the color of light that reaches you from a star to the spectral lines of the same color in the laboratory, which is your sample, something that's not moving, if they match, then you know that the star is not moving. If the star was moving away, it is possible to calculate the wavelength of the spectral lines that you can see from the star that's going away and compare it with the wavelength of the same color of light in the laboratory. The wavelength of the star that's moving away is going to be bigger, because when something's moving away, emitting the waves spread out. Okay, so you know that the star or the galaxy is moving away. If on the other hand a star was approaching us, then what happens is that the waves bunch up, and what you're going to get is a shorter wavelength. Now, how does all that tell us? How can you know by the spectral lines? So I'm just going to draw that little thing here. White light actually consists of your 7 colors. So at one end you have your red end, okay, and then you have your yellow, orange, blue, green, and the other end is your blue end. So you got your red end and your blue end of the spectrum. Okay, so blue is the shorter wavelength, L is the longer wavelength. Now the thing is, a little change in the wavelength will amount to a change in the color of light. So if your spectral lines, if the star was moving away, if you compare it with the laboratory sample, all the lines that match each other in the spectrum will be shifted towards the red end of the spectrum, because red has got a longer wavelength. If the star was approaching us, all those lines will be shifted to the blue end of the spectrum. So if it's shifted to the blue end of the spectrum, we call it a blue shift. And if it's shifted to the red end because it's moving away, we call that a red shift. Okay, so that's just a little extra before I start doing this question. Now this question number 2 in Doppler effect, says a distant galaxy is rich in oxygen atoms, and an analysis of its spectrum indicates the wavelength associated with one of the intense spectral lines for oxygen has a wavelength of 5.13 times 10 to the power of negative 7 meters. So that's the apparent wavelength, the wavelength that you're getting from the star, from the distant galaxy. Okay, now, and also the wavelength in the laboratory of the same spectral line is 5.01 times 10 to the power of negative 7. Now, if you compare these two wavelengths, they're not the same, they're a bit different. So this longer wavelength suggests that the galaxy is moving away. Okay, now the first thing we have to do is calculate the frequency of the galaxy line. The thing is, this is to do with light, and the speed of light is 3 times 10 to the power of 8 meters per second. So we just go frequency is speed divided by wavelength, and this is the apparent frequency, and then you have the actual frequency. Okay, so that's and then since the apparent frequency is lower, then we know that the galaxy is moving away. So you can argue this either by the apparent frequency or the apparent wavelength. What is it that doesn't change? The speed of the wave itself. Okay, so you just need to keep that in mind. So what we have to do in this question is calculate the speed of the galaxy. That's the speed of the source. Okay, so I've just started doing it, haven't quite finished, just to save some time, me working out and putting numbers into the calculator. So the formula that you use is F dash equals F times VW divided by VW plus Vs. So that's your apparent frequency equals the actual frequency, which is a higher one, times speed of light divided by speed of light plus speed of the galaxy, which we don't know. Okay, so what we do is cross multiply, so, or in other words, multiply both sides by what's in the denominator. So you get 3 times 10 to the power of 8 plus Vs times that equals that. So the next step, yeah, you can see what's at the bottom. So you just go 3 times 10 to the power of 8, so factorize, so times 847 times 10 to the power of 14 plus 5.847 times 10 to the power of 14 times Vs equals that whole number. I'll just put that whole number into my calculator so I'm not getting so many numbers. So it's 5.988 exponent 14 times 3 exponent 8, and I get 1.7964 times 10 to the power of 23. 1.7964 times 10 to the power of 23. And if I just get one number for this, so I get 3 exponent 8 times 5.847 exponent 14, I get 1.7541. 1.7541 times 10 to the power of 23 plus 5.847 times 10 to the power of 14 times Vs equals 1.796 times 10 to the power of 23. Now I'm going to just transfer that up because I don't have any more place on my whiteboard at the bottom. So I'll just rewrite it here. Let's use a different color so you know. So what I have there is 1.7541 times 10 to the power of 23 plus 5.847 times 10 to the power of 14 times Vs equals 1.796 times 10 to the power of 23. Okay, so I just want to make that the subject of the formula. So I get 5.847 times 10 to the power of 14 times Vs. Oops, this board is falling. Okay, it's okay now. Okay, equals 1.796 times 10 to the power of 23 minus 1.7541 times 10 to the power of 23. Okay, so how much do I get? 1.796 minus 1.7541 equals 0.0419. 0.0419 times 10 to the power of 23, and so Vs equals that number divided by here, 5.847 times 10 to the power of 14. So Vs equals, so 0.0419 exponent 23 divided by 5.847 exponent 14, and I get this big number. I get 716.6068 meters per second. 1, 2, 3, 4, 5, 6. So I'm just going to write this as 7.17 times 10 to the power of 6 meters per second. So that's the speed of my galaxy. So I hope that made sense. Bye for now.